Hi, this is Professor Cummings, and I wanted to do a brief video today talking about how to do basics on gearing. Now, gearing is one of the most versatile machine elements that you're going to be able to use, and I thought it would be a good video just to go over some of the most fundamental aspects of gearing. Now, I'm going to speak in generalities, so I'm not going to get into things like helical gears or bevel gears or, any herringbone gears or anything else that can get to too much complexity. So I'm going to try and keep this talk pretty universal. So go over some of the fundamentals of gearing, how they're utilized, what you need to take into account when you design a gearing system, and what other aspects of what gears can actually do. And from there, you can build onto that knowledge to much more complicated gearing system. So this is just the fundamentals of what gearing is. Everybody's been in a vehicle. Everybody's had to change speeds. Everybody's had to use the power differently. So this is some of the things that I think this particular system can demonstrate. So if you've ever been in a car, you've ever been in a pickup truck, you've used your gearing system, your transmission system to do three basic things. And this is what gearing systems are all capable of. They're capable of changing the power, the amount of power from the input to the output, or come out as a different type of torque. They're able to change speed, which is the reason you go from first gear, second, third, fourth. And they can also change direction. And in this case, direction is not just going from reverse and forward, but also able to utilize gearing systems that can actually go, 90 degrees or any number of degrees, not just linearly. So gears have a lot of ability to actually transmit and change the direction of energy and just change the nature of how the energy is going to be used to make it more mechanically useful for you. Now, what I want to start off with is showing you this schematic of gears. So the benefit of this particular diagram is that it gives you some view of what all goes into gears and to the mechanics of the gear. So what we have here is the upper gear. You just call that the pinion. The smaller of the two is typically known as the pinion. So we can identify that as a P. And the lower of the two, the bigger of the two, is a gear. So that is typically identified with a G. And sometimes these are labeled A and B. Sometimes 1 and 2 are they're numbered. But for all intents and purposes, we're going to say P is the pinion, G is the gear. Now, some of the more important features of the gearing system I want to start with is the shape of the gear tooth, which is known as an involute. Now this involute, like I said, is the shape of the tooth, and it is that rounded profile of the gear tooth itself that when in mesh with the other gear, the pinion to the gear, it allows for a smoother transition of power. So it's got this radius that's designed into the tooth so that it makes contact and maintains that contact, over a longer period of time. So the transmission of the power of the gear from pinion to gear or gear to pinion is smooth. The gears typically won't disengage when you have an involute until the next gear has actually come into contact. That's one of the reasons why it's such an important shape in the gearing system. So that involute. The next thing I wanted to talk about was the pressure angle. Now, the pressure angle is one of the things that people typically don't think about. But what it is when gears are actually in mesh, it is this angle here, pressure angle, that forms between the line of action and what is known as the pitch line. And the pitch line is simply the tangent of the two pitch circles, and all the pitch circle is the point of contact between the involutes. So you've got a gear with a pitch circle, which is simply the midpoint of the involute, and where the involutes actually meet is known as the two pitch circles. That transition point creates known as a pitch line, sometimes called a pitch plane. Now, the angle between this pitch line and this line of action, where these two actually meet, is known as that pressure angle. And this is important. The reason I'm going through all this with the pressure angle is because this dictates the direction and the composition of the forces that the gears act on each other with. So it can actually, and that ratio between the different forces is dictated by that pressure angle. So this can actually play into an issue with the amount of pressure on your drive shaft, your axle, your whatever component that these gears are riding on. So it actually can be a big factor in your gear design. So that pressure angle and that line of action are very, very important. Again, speaking of the line of action, it's simply the straight, defined as the straight line passing through the pitch point and tangent to both base circles. So here we have this area here, which is just the pitch point, and where that contacts is the line of action. Again, that's dictated with that pressure angle, or tied in with the pressure angle. And that line, there we go, the line of action. Now the pitch circle, or the pitch diameter, again, that is, the pitch circle is just the circle defined by the points of contact of the two meshing gears. So where these come together, you actually create the pitch circle. Now, there's a lot more to this. There's an addendum, which is the top of the gear. There's a dedendum, which is the bottom of the gear. There's the root and the fillet. All these things are, important, but these are actually going to come up in a lot of our future calculations, and they play a major part in gear design. So when you design a gearing system, these are the things that you're definitely going to end up touching on, as well as some of the others, but these seem to insinuate themselves all the way through gear design. Now, when we look at those gear features and we can see the static picture, we have here is another GIF, and we can see how these things actually play out. So we have this blue line here that actually is our line of action. If I just trace that over, so you can see this is the line of action. We've got our two pitch circles between the pinion and the gear, which actually meet here and here. And so this is the way that the pitch circles actually meet, your line of action. And one thing that's not shown on this picture is this pitch line. Now, one important thing, that's not a very good picture, but one thing that's important about this pitch line is that this is the area where the force actually travels through the gears. So this is the force, so that's where the force actually becomes tangent to the two gears, where that pitch circle meets, and actually transmits and causes the pinion or the gear to force the other gear to move. So this is important. And also one thing to get from this picture is, if you notice the curvature of that gear tooth, that's the involute shape. And as this pitch line, or this pitch point in the line of action transmits, you can notice that it's a very smooth transition. And that is because of the involute shape of the gear tooth. So you can see all of these different things laid out again. So this is your involute. This is the pitch plane, or the pitch line. So it's traveling through this direction. You got your pressure angle, and here you got your two pitch circles where they intersect. So this is how the gear, from the last schematic, how the gear geometries and the gear features actually lay out. And this picture here over on the left is just giving you a visual as to how these things actually interact in real life. And you can see the benefit of that involute. If these didn't have that involute shape, it would be a much more jumpy, much more abrupt transmission of power between the two. And we'll get into more on that, but just keep this in mind as we move forward. So another feature of gears is, you notice this is just two different gears hooked up, and actually these are helical gears. The rest of the gears have been spur gears, and that's really what we're talking about. But this GIF will actually do. If you look at these two gears, we don't know which, but one of them is actually driving and one of them actually is driven. So one actually has power, the other one is transmitting power. And if you notice that they're moving in two opposite directions. So one is moving clockwise, which forces the other to move counterclockwise. And this is just a common aspect of how gears are designed. One gear comes in a mesh with the second gear, and it pushes it into the opposite direction. Now, the way to get around this is with a concept called an idler gear. And one of the benefits of an idler gear is it forces the gears to change direction. So if you have a scenario where you want two things going in the same direction, say if you have a motor that's going clockwise and you want an output that's also going clockwise, what you can do is use an idler gear as a way of making this direction change to where you want it to go. Another purpose of an idler gear is to help fill in gaps, so you might need multiple idler gears. And the benefit of an idler gear is it doesn't actually change the design of the system as far as the calculations go. They actually fall out because they just take into a certain part of the gear train or the gear values, and they just actually neutralize themselves as far as the calculation go. But by able to change direction, this is one of the great benefits of an idler gear. And if you look at a manual transmission on a car, or even an automatic transmission, there is an idler gear that comes into play in order to make the transmission go from forward to reverse. Another thing to think about or to keep in mind is the ability for gearing systems to take a rotary motion, like from a motor, and turn it into a linear motion. And that is oftentimes done with a rack and pinion. So what you have is a pinion here, which is actually powering the system. And then you've got a rack that actually gives you a linear direction, a left and right direction. And a lot of your steering systems have this sort of a system in it. So you've got a gear system that actually can give you a rotary motion from the steering wheel, and it uses a rack or tied into that pinion to give you a linear motion into your steering mechanism. Now, another aspect of your gearing system is the idea of a compound gear. Now, keep in mind, you have gears that are tied together, which would make them a compound gear. They have a common axis. And when you keep that in mind, you actually know that these two gears actually have the same angular velocity. So let's put some numbers on these. We'll call the bigger gear gear number 1. The second gear that's in tandem with it is gear number 2. And then you've got this gear, the output gear, we'll call that gear number 3. So gears number 1 and 2 have a common angular velocity, meaning when gear number 1 goes around one revolution, gear number 2 goes around the same revolution. Now, because of their different diameters, gear number 1 and 2 have completely different tangential velocities. So and that's one of the other benefits of a compound gear. So if you have a certain velocity that you're trying to manipulate, or a certain type of torque that you're trying to manipulate, or a certain type of speed that you're trying to manipulate, you can actually use compound gears in order to make a step down. This is oftentimes when you have step down gears or step up gears, multipliers, sometimes they're called reduction gears. You're using compound gears. And because of this difference in the two diameters, you can actually step the tangential velocities up or down accordingly, because the ratio stays constant. So what you have here is you've got two gears on this compound gear that actually have a common angular velocity, but proportionally different based on their radiuses or diameters, tangential velocities. Here you have these two gears, and we're not going to make any assumptions on their diameters, but they do have, regardless of that, a common tangential velocity. Same that you would see with this rack and pinion. So that tangential velocity translates to the same tangential velocity here, and this is still along the pitch line. Both of these are along their own pitch line. Now, keeping that in mind, this relationship between the velocity and the radiuses of the gears, where 1 and 2 have a common angular velocity, measured in RPM or revolutions per minute, and they have a common ratio relationship between the tangential velocity and their respective radiuses. Now, this is also another important concept to keep in mind when we actually go into further gear design. Now, what this also tells you, again, is that the tangential velocity is common between gear 2 and 3. So keep this in mind, that the differences in their tangential velocity is dictated by the differences in their radiuses, which is going to have a very important impact in the future. Now, when you put all these together, compound gears, idler gears, you're able to not only do a lot of manipulation in terms of stepping up and stepping down velocities and torques, you're able to keep the directions in whatever desired output. So a series of gears and gear values put together can actually give you the desired output. And if you can shift these gears around, much like in the transmission of your car, you can end up getting a whole array of different types of inputs and outputs that you would like. So these can be very versatile. And when you put these gears together, in order to create this system, you end up with another concept known as a gear train. Now, speaking of gear trains and thinking of all those ratios between velocities and diameters and angular velocities, that gives us one new concept I want to bring up, which is a velocity ratio. Now, the velocity ratio is something that you can calculate between two meshing gears. Now, in this example, you can see you got a bigger gear with 60 teeth and one that has half the number of teeth, so 30 tooth gear. The bigger tooth is the driver. The smaller gear is actually being driven. Now, because of these differences in their radiuses and in their number of teeth, you're going to get a very predictable output. So as you can see here, this smaller gear, this gear that's got half the diameter and half the teeth, is actually going at twice the velocity of this bigger gear. That is what we think of when we think of a gear ratio, or excuse me, a velocity ratio. We identify that as VR. It is the ratio between the angular velocities of the pinion and the gear, or the radius between the pinion and the gear, or the number of teeth in the pinion and the gear, and they give you this very predictable calculation for setting up your velocity ratio. So if you know, or if you've decided on how big the gear you're going to use, the type of teeth you're going to use, and the number of teeth that are going to be on there, you can actually calculate how much you're going to step the velocity of one gear up and step it the other gear down. So that's a very important concept. So in this particular gear setup, we have a velocity ratio of 2. We're actually doubling the speed, or the angular velocity. You know, tangential speed is the same, but the angular velocity is different because of those two radiuses. And which leads us back to the whole idea of the pitch line, which is just the tangential velocity between the two gears. And you can see this is based on the radius and the angular velocity. Now, when you've got two or more gears, together you end up with what is known as a gear train. So now we can see we've got a gear train, you know, where we've got two gears in mesh here. You've got a compound gear between C and B. And then you've got an output gear at gear D. So you've got 4 gears, you know, 2 in mesh, or 2 sets in mesh. And putting these together, you end up with a gear train. So it's just 2 or more gears operating as a system. So that gives you another calculation that you can use, which is the train value, which is the ratio of the input speed of the first gear in the train to the output speed of the last gear in the train. And this is another method you can use to design your gear train to get a desired effect. Now, the way you would calculate this, or another way to calculate this, is the product of the different velocity ratios. Now, remember, the velocity ratios was 2 meshing gears. So in this case, you'd have a velocity ratio between gear A and gear B, and a velocity ratio between gear C and gear D. And the way you could calculate this based on the number of teeth or the different radiuses is just take the different velocity ratios and multiply them together, and that gives you a train value. Now, once you know this train value, you can use this to understand what your system is going to do, and you can actually manipulate it. You know, if you need to add teeth, or a gear with more teeth, or a gear with a different velocity or a different diameter, and end up getting the output that you're desiring. Now, we do more than just try and change speeds with gears. Gears also are used to do a lot of mechanical work. You know, if you have a vehicle and you have a lot of heavy load, you might need to shift it to a lower gear. If you're on a surface and you need to get better traction, you might need to shift the gears in order to get more force. So it's not always about getting more speed out of the system. Sometimes you need to be able to transmit more torque throughout your system, or less torque, which allows you to get a little more velocity out of the system. So again, looking at this schematic, a different schematic, you've got a pinion and a gear. Pinion and a gear. You've got a line of action, and along this line of action you can see you've got a force, and then you've got this WR and a WT. And you also have the pitch circle and the base circle. So this pitch circle, so all these things come into place. So this is where the teeth are actually connecting. And remember, it's this tangential force along the pitch line that actually forces one gear to move the other. So let's look at some of the forces that are going to be taking place here. The first force is this force that goes along the line of action. And that is what's known as the normal force. It is normal to the involute of the tooth. So it goes along that line of action and comes and intersects with the involute, and it's normal to that involute. And all this is the resultant between two more forces. It's the resultant between this force, which is the tangential force, which goes along the pitch line, and which is actually responsible for supplying the force that actually causes one gear to move the other. Then you've got a third force, which is the radial force. Again, this is actually works between the two axes. This is actually the forcing the two gears to have a load between them. Actually, it's literally pushing them apart. Now, and here you have this normal force, which is simply the resultant force between the two. So and you also have the pressure angle. The pressure angle, which will be here, which is going to become part of the equation later. So all of these things come into play with how the force is actually moved through the system. And again, this is just showing you that the normal force is just a resultant between the tangential force and the radial force that acts between the two gears. Now, the way these are calculated, you can calculate each one of these. The radial force is simply the tangential force times the tangent of that pressure angle. And the normal force, other than the sum of squares, you can calculate that as that tangential force times the cosine of that pressure angle. Now, how do you actually measure the tangential force? Again, this is something that you can't go out and measure it. You can't put a gauge on it, so you need to calculate that too. And the way to calculate that is with the torque you're putting into the system times the radius of the gear. So if you have the torque divided by the radius, you can calculate what that tangential force is moving the system. So think of it as calculating a moment. The radius and the force being applied gives you a torque. And the way you would calculate that torque is just simply, doing a little bit of algebra. So the force times the radius. And another way of getting that is if you know the power that you either need in the system or the power that you're imparting on the system with a particular motor times the torque and the rotational speed. In this case, it's defined as N, so the rotational speed, you can get the power. So if you have the power on your motor, and you know how much torque you're needing, or you know how fast the system has to go, you should be able to calculate the force that you're actually imparting between the gears, your radial force, and then your normal force. And depending on the gears you bought, you would know the pressure angle. So this is the way you would actually calculate the force going throughout the system. And once you've got that, you can start designing things like your drive shaft, because you'll be able to calculate your bending forces and the stresses that you're going to put on that shaft. And this is how you start considering things like the material that you make the gear from, because you're able to calculate all the forces that are taking place on this system, including the gear. Now, when you think about a gear system, keep in mind, everything is going through the teeth of the gear. And not only going through the teeth of the gear, but with the involute, it's actually between two radiuses, two curved surfaces. So it's actually coming in at a point. So a lot of this force is coming in a very specific place. So that's a whole lot of force happening and creating a whole lot of potential failure. So let's talk about this failure. Now, what you have here is a finite element analysis of gears in mesh. As you can see, if you ever know anything about finite element analysis, the red is actually showing you points of high stress on that gear. And you can notice it's actually the highest where the gear is actually contacted, and also down here at the base, or the root, the fillet of the gear, or of the tooth. So these are the high stress points, and this is the areas where you're actually going to have potential for failure. So what are these failures called? The first point, right where the teeth meet, is called a contact stress. And this contact stress, again, it is a point where they can potentially fail. The failure will take place in the form of pitting and galling. Because there's a lot of stress here where they're put together, and at some point in time, that entire system is dependent on this one point of engagement. So it's important to understand, what is going on there. This could help dictate the size of the gears that you use, the material you use, as well as the heat treat. Heat treating is very important in gears. So this is where you get a lot of gears where you're actually doing a lot of surface hardness because you want the gear to have a lot of toughness within, but you want it to be very hard at its points of contact. Another source of stress is down here at the fillet, which is the bending stress. And this is kind of intuitive as the gear is actually transmitting force. And remember, the tangential force is actually going across this way. So this is what's making the gear move. And as this is being pushed, it's actually creating stress down here at the bottom because this is where it's going to want to bend, hence the name bending stress. And it's just the stress at the root of the gear here at the fillet where you can see a potential fracture. And again, this is another thing you keep in mind when you set up the gear and to do any of your detailed designs, as well as the design of your drive shaft and any of your axles. So this is Professor Cummings, hoping that this was valuable to you in terms of an overview on gearing. So we didn't go into a whole lot of details, and there's a lot of different ways that gears can be designed, a whole lot of different styles of gearing, but at least this is an overview of the gearing and the things that actually play into your gear design. And if this was helpful to you, if you got anything out of this, you can go ahead and subscribe to this channel or visit me on Google+. And from there you can actually see how things are going to be up to date. And any other, engineering and manufacturing topics that I go over, you'll get a first-hand ability to see them and listen to them right off the bat. All right, thanks a lot, and thanks for listening.